Thanks, Ananya. Can everyone hear me all right? Okay, good. So my plan for today is to basically just talk about cryptography and see where this goes. Okay. So can you all tell me what exposure you've had to cryptography before? How many of you have seen a little bit of basic cryptography? Okay, quite a few. So maybe you can tell me like what you have seen. Okay, so I think that there'll be a divide between those in school and those in college here, right? So, okay, hashing algorithms. All right. So, let's do this thing where we start from the very basics, okay? And we'll see how far we can go. So, I've met you all here in this room for the first time, right? None of us have met before. And now let's say that, there's one of you, let's say the girl there, that I would like to communicate in private with. Okay. So now the only option I have to do this communication is right here on this platform through this mic. So I've never met her before. I'm seeing her for the first time in this room, right? And we have no, there are no keys that have been exchanged or anything of that sort. So is it possible for me just by shouting in this room to exchange messages that only she can understand and nobody else can? Is it possible? Everything I say can be heard by you, right? And everything she says can also be heard by you. So it seems there is no asymmetry here, right? I mean, it's a broadcast, what's called a broadcast channel. So it seems like this should be open for all. So do you think there's any way in which any pair of us, any pair within this room, who can only shout out loud, right? It's too loud. How should I do it? Is this better? Okay. So, yeah. Is it even for me, it was too loud, but yeah, it's quite a arrangement you have. Yeah, I feel like I'm on a spaceship or something. So, yeah, can we do it? No, so no jargon. So the basic rule for today's talk is that we don't use any jargon, okay? Everything is from first principles. So the problem that I stated is completely from first principles, right? We've met here while I'm on this platform. Everything I say, you can hear, all of you can hear, everything you say, everyone can hear everything, okay? So now we want to exchange messages in private, just the two of us, let us say. And there is no prior agreement on anything. Okay, and we're going to do everything in today's talk completely from first principles. So now, yeah, without using any jargon, just from first principles, you need to tell me whether you think this is possible or not. Yes? Yeah, very good. So that's a very logical reply. So she says that, this cannot be possible because there's no asymmetry. Everything I say can be heard by you. Everything you say can be heard by everyone else, So how is it that two people can suddenly start talking in private? Does anyone here think it is possible? How? But I don't accept that as a reason. You have to tell me, you cannot say I've heard about something. Yeah. So like I said, so the basic principle of, being a scientist is that everything is always from first principles. Okay. So we don't go with any hearsay. We work everything out for ourselves. So, okay. So far, I have nobody who has any, does anyone think it is possible? Yes. There is no such language. We're going to use English. We've seen each other for the first time. We don't even know if there's any such language, right? But you're thinking of an encrypted channel. So I like the way you're thinking. But no, I'm not cheating. There's no cheating. Is it possible? Yes. But then my facial expressions, everybody can see, right? Good. So everybody is trying to find sneaky ways to change the model. But I'm a very honest person, no cheating. The problem that I stated is the problem that I have, no cheating. So I'm not going to do like this and then, make lip movement towards her. I'm not going to do any of that. Yes. Anyone else? Anyone thinks that this is possible, that this should be possible? Actually, what she said sounded really like a good reasoning, right? There's no asymmetry. So I'm going to tell you that it is possible, and I'll show you how to do it. I'll show you one way. There are many ways of doing it. And more importantly, what I'm hoping to convey in today's talk is, this excitement, this sort of magic that is there in cryptography, which is really, it's like the art of paradoxes. It's the science of what should not be possible. That is cryptography. So, you ask a question, and anybody thinking in a reasonable way will think that no, this cannot be possible. Okay, just by using reasons like what you gave, and I'll address the reason you gave. So, we start out by asking a question. It seems like this should not be possible, and then in cryptography, we make it possible. So, in particular, in this situation, one moment. So, Ananya, can we stop people from coming in because it's very distracting? Yeah, just maybe we can shut the door. No. Okay, maybe I'll just clip it. This is better. Maybe this is better. Yeah, so you see, the basic thing I want to say even before talking any crypto is please always be on time. It's very bad to come late and, disrupt the audience and then we're talking amongst each other, right? So in my classes, I never allow it. I have made already some exception here, but no more exceptions. Okay, so who's in, who's not is not. So the question that we were asking is, for the sake of those who came late, is, in a broadcast setting where everybody can only shout and anything that anybody says can be heard by everybody else, is it possible for two people who've never met before, who have had no prior agreement, is it possible for them to exchange secret messages? This is the question. And the reason that you gave is that it should not be possible because there seems to be no asymmetry in the system, right? So everybody is equal here. So why should it be that two people can suddenly talk in private? So the reason that we think actually that this is possible is because we conjecture asymmetry of computation in the universe. That is where the asymmetry comes. We conjecture that there exist one-way functions. What's a one-way function? First of all, what's a function? Like a mathematical function? It need not. Okay, so let's think of a domain and a range. Okay, and there's some function f that takes any point from the domain and maps it to some point in the range. Okay, so this is our mathematical function. And what's a one-way function? Just like the name suggests, a one-way function is a function that is somehow one way. So it's easy to compute in one direction, but it's very hard to go back. Okay, so let's think of a function f, okay? And this is going from some domain to some range. This is my domain, this is my range, okay? And any point in the domain can be mapped to a point in the range. Let's think of permutations for simplicity, okay? So that means that every point in the range can also be mapped to a point in the domain. But the problem is that this is very hard. This is still quite noisy, right? I'm not sure what to do. Do you have a different mic? Or let's leave it. I'm fine with it. No worries. No. Should I just take it off? Let's continue. Okay, so the 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 definition of a one-way function, I say definition, but actually I'm being very hand wavy, right? Is that I can go from the domain to the range fairly efficiently. I can do this quickly, okay? But in taking a point from the range and mapping it back to the point in the domain is somehow very hard. Now, this is the sort of asymmetry that, we are really assuming exists in the universe. Why is it hard? I mean, we don't know how to do it in any easier way. So it's a conjecture. So there are functions that we conjecture are very hard to reverse. Now, why do I say conjecture? Why cannot we prove it? Because this is very intimately tied to the famous P versus NP question in computer science. Okay, so for example, if I could prove that one-way functions exist, then this would mean that I have solved the P versus NP conjecture, which, as you might know, is a very famous open problem in mathematics and computer science. So we have to conjecture that these one-way functions exist. Yes? No. Good question. No, the reverse is not true. It could be that, let me not go off on that tangent. Okay, so yeah, that's a very good question, but it's not true. So, this is my conjecture. Okay, and now I'm going to, let us say, I'll give you an example of a one-way function, a conjectured one-way function. Okay, and using that, we'll try to see how we can exchange these secret messages. Okay, so now I'm going to think of some group G, okay, of finite prime order. Now this I'm just telling you a few details here. This is not, if you don't know too much about groups, don't worry about it. Just think of it as a set of points, okay? So think of it as, integers modulo some prime number, for instance, okay? Now, this group here, I want it to be generatable by some small g. So now, again, let's just think in very simple terms, okay? So if I think of integers, okay, I think of integers as a group under addition. What is a generator? 1. So 1 plus 1 is 2, right? 1 plus 1 plus 1. So using 1, and then the 1 will have an inverse, right? So that's minus 1. So using this, I can generate the integers. Now here also, I'm thinking of a group. I haven't really specified what this group looks like, or what this generator is exactly. But let us just think of a finite cyclic group. What I mean by that is that, there is some group capital G which has a finite number of elements, and I can generate all of them using this one element small g. Okay, is it fine? So G is the generator. Okay, now G is the generator, and I'm going to give you a conjecture. Okay, so if I give you small g and I give you G to the x for some x, okay, it is hard to find x. So what does G to the x mean here? So So, there is some operation that I can do on G. Let us think of this operation as being denoted by multiplication. So that means I can do like for integers, when we talked of addition, we were talking of, plus as the operator. Let's think of multiplication as the operator. It's an abstract object, so, I could call it what I want, this operation. But what this is saying is that I have some set of elements, right? And I have a generator. And now using this generator, I can generate all the elements of capital G. That's just by definition. Okay. So G times G times G times G, if I keep doing, right? If I do it X times, I get something which I call G to the X. Correct? And now if this group is sufficiently big, right, then this X could be quite a big number, right? So, let us say it could be 500, it could be 5,000. So it really depends how many elements this capital G has, but this small g should be able to generate all of these elements. So this X could be a very big number. Now, I want you to think a little bit about, this conjecture. So what I said is that given small g and given, g to the x for some x, it is hard for me to find x. Now, this is not always true, right? Like if x is a very small number, suppose I'm only choosing x from the set 1 to 5, then I can figure out which my x is, because I can do g to the 2, g to the 3, g to the 4, g to the 5, and I can compare. No, so I'm thinking of a group, right? So I'm just taking the generator and applying the operation to it in order to generate the other elements of the group. What? So for integers, I gave this example, right? Like where the generator is 1, and then 1 plus 1 is 2, 1 plus 1 plus 1. No, so the reason you're getting confused is that you're getting stuck with addition. But I'm saying that, I'm just defining my group operation as multiplication, right? So I could do that, right? I'm just telling you that I'm taking some group here, right? And I'm defining the operation as multiplication. So now what do I have? I have this conjecture which says that given g and g to the x, for some x, it's hard to find x. Now, this conjecture is not precisely stated because obviously it's not going to be true for any x. Okay. But if I choose my group G with a large enough order, that means that I'm choosing x from a sufficiently big range, then pretty much, if I choose x randomly from a large set, then pretty much the only thing I can think of doing is try out brute force different values of x, and this would take me too much time. Okay, so I'm being very loose over here by the group is given using the generator. The generator is just described, I mean, using bits or something, like what I didn't understand. I mean, if I have ZP star as my group, then, I have one element in that. What's the question? What do you mean, what form? I mean, I have a group, I have a generator, right? I sort of operate on this generator many times. I'm not going to write it as G2. I'm not going to give you a pair G comma X. I'm taking this G, I'm operating on it, right? So if my generator is 2, let us say, okay, and if my X is 3, I'm doing 2 times 2 times 2 and giving you that number. It doesn't matter. You choose your encoding. Whichever encoding you love, I'll give it to you in that. It doesn't matter. Yeah, I mean, think of bits, think of, I don't know, integers. I mean, it doesn't matter. Like what encoding you use doesn't really matter. So I was deliberately being vague about the group here because there are many possible groups that one could use. But like if I take ZP star for instance, right? So P, I want it to be like a very large prime, and I'm taking ZP star. So my operation is multiplication. Okay. So now I will take a generator of this group, right? And then I will just multiply it x times, and I will get some number, and I will give you that number in your favorite encoding. Okay, so don't get hung up on this encoding. In fact, I would like to take this opportunity to say that we may in this domain, it's useful to think more abstractly, right? So it doesn't really matter like which encoding I use, binary, ternary, hexadecimal, it doesn't really matter. Yes. Suppose they are, but what does it matter? Yeah, so you can pick any group and any generator of that group, and this is the problem that I'm stating. Okay, so choose your favorite generator of the group, and then now we are in business, right? So the problem that I stated, yeah, I can give you the order of the group in this case. See, this is why I was saying that I'm not being specific about the particular group. Okay, so since we asked for a particular example, so when I stated the question, I said, let's think of finite prime order. So, it definitely needs to be finite. Prime order, I said, to make it simple, right? You could, yes, ZP star has order P minus 1, which is not going to be prime. But this is why I did not want to go into like one specific group description. Yeah. Okay, fine. So, let's just think of uh, you know, think of ZP star if you want to. But like I was saying, I did not want to go into one specific group here. Okay. So the question here is that given G and G to the X, can I find X? And what is a simple way to solve this problem? Just brute force, right? So, do G squared, G cubed, and so on. But because I have taken the order to be very large, right, this is going to take me too long a time. Okay, and I can choose the order to be sufficiently large that practically kind of running this algorithm of finding this X is going to take me, I don't know, more than the age of the universe, like definitely more than my own lifetime, right? So the trivial algorithm is very inefficient. Now, there are a few somewhat better algorithms that are known for this, okay? But really speaking, we don't know how to solve this problem in any efficient way, okay? And this is called the discrete logarithm problem. Okay, so what is the conjecture? The conjecture is that given G and G to the X, finding X is hard. Okay, here we are going to assume that X is being chosen randomly, and that the order is large enough that I cannot just brute force and find all, like I cannot just brute force through all the powers and check. Okay, so this is the problem. Yes? Any questions? Okay, so good. So now this is the conjecture. And now here, we already have some asymmetry that is coming in, right? What is the asymmetry? There is no asymmetry in who hears what, but there is an asymmetry that is being conjectured about the universe and its computing powers, right? So we are conjecturing that it is easy for me to compute g to the x, right? By the way, how to compute g to the x efficiently also requires a little bit of thought, right? Because if x is so big that I have to do, and I have to only do g squared, g cubed, and so on, then also computing g to the x should be very time consuming. But I'll let you figure this out offline. Okay, so computing g to the x efficiently can be done. Okay, but we don't know how to reverse it. Okay, so now this is my conjectured hard problem. So now let's say that we all agree that this problem is hard to solve. So now can anyone think of how I might use this to crack the problem that I originally stated? So I want to start communicating in secret with one of you over this broadcast channel, and I want to just use this hard problem in order to assist me. Yeah, it's not that easy to come up with, but I want to I want us all to stare at this for a while and try to think if we can do something. What? There's no message yet. Yeah. How will the other person decode it? So someone has to. So remember that everybody has the same power, right? So I cannot choose if I choose a secret and put that in the exponent and then publish that, right? Or sort of write it on the board over here. Everybody can see that, right? But I want one person to be able to open it and read it, and nobody else should be able to. So what are you saying? Okay. Okay, good. So what is being suggested? So this will not exactly work, but this is on the right track. Okay. So one of the reasons why it does not exactly work is that this x that I need to choose for this problem to be hard should be, like I said, sampled from a big set, right? But my message need not be random, right? Like I want to send a particular message. So it's not that I can sample my message at random. I want to send a particular message. So I don't know what you mean by salt here. Yes. So that is what I was saying, that it will not exactly work with X as the message. But what we can hope to do is that we can hope to agree upon some common value first. Okay. And once we agree, sorry, which value? Yes. So once, but wait. So you have to be careful here, because when we say that something can be public, we have to make sure that it's not leaking any secrets. Okay. So we have to make sure of that. So what we'll try to do here is that, since we said this problem is hard, okay, so I'm going to think of some x in my head. Okay. I have to pick it at random, right? And I will, let me call this as y. So let me call this as x0 and let me call this as y0. Okay. So I'm going to pick some x0 in my own head. I'm going to compute g to the x0 and I write down y0. Okay. So this y0 will be written on the board. So everybody can see this y0. Now, what should the other person do? The other person, so let me erase this to avoid confusion. So what the other person can do is similarly sample a random x1, okay, and compute y1, which is g to the x1. Okay, and now once again, what I publish is only y0 and y1, right? So having published y0 and y1, now how will I use this to proceed? So basically the point is that I know x0, I don't know your x1. You know x1, you don't know my x0, but you know g to the x0, right? And I know g to the x1. Everyone has g. They have g. I'm giving you g. Yeah, g is known to everybody. So what is written on the board is g, y0 and y1. Okay. So now what will I do? I have g to the x0. So let me say that I am party 0. Okay. So I have x0. Okay. So this is what I have. Okay. And let's see what is it that you have. Okay. So I have x0, g to the and g to the x1. Right? Because we wrote down on the board y0 and y1. Yeah. So I have x0 and g to the x1. You have x1, right, and g to the x0. So now both of us can compute g to the x0, x1. You see? So now what did we do? We managed to have a sort of a value which only the two of us know. That's the main point, right? So you see where the asymmetry came in. The asymmetry came in the asymmetry of computation. So I just had to have a value in my head. You had to have a value in your head, right? And now using these two secret values, we were able to use publicly declared values in order to agree upon this random value g to the x0, x1. And now using g to the x0, x1, I can mask it to any message of my choice, right? So if I want to now exchange a message with this person, I can just choose my message M, right? Map it to the correct space. Let's assume that, that's not something we have to worry about. And then I will just add this value to it. And again, I'll write it on the board. Now you alone know how to subtract this value because you alone know this mask, right? So now you can recover this value. Who? See, you picked it, right? So let's say we both are talking. Is this protocol or this algorithm clear to everybody? I have x0 in my head. You have x1 in your head. Yeah, you will make g to the x1 and you will not just give it to me. You will give it to everybody. No talking between yourselves, please. Please speak up if you have any comment or question. There any? what are you talking about? You're trying to, so yeah, I don't know what is your question. So yeah, I mean, I don't, y'all are talking to each other. I have no idea what you're saying, so I cannot help. You're trying to solve the discrete log problem, right? No, it's good. Is that the, yeah, yeah. So I will, you should think about why that does not work. It's because you cannot really compare, right? Okay. So let's talk about this offline. Okay. So is the protocol clear? So did you have a question? It's clear? Yeah. So using this idea, right, what were we able to do? We were able to start exchanging secret messages, right, within a crowd in a way that only uses the broadcast channel. Please don't talk amongst each other, right? So this is a very a very crucial building block in cryptography. It's called key exchange. Okay, and this particular protocol which I showed you, this was discovered by Diffie and Hellman, I think in 1979 or thereabouts, and it was considered revolutionary enough that they received the Turing Award for this. So it is highly surprising, right? That's one of the things that I wanted to outline, is that the questions that we ask in cryptography, right, the logical answer to that is that this should be impossible. But yet there are ways in which, this becomes possible, and it makes use of these conjectures which we can make in mathematics. So in some sense, it's a very it's a very optimistic field in some sense, because things that are hard are now something that you want things to be hard, right? So in algorithms, you want everything to be efficiently solvable, you want an efficient algorithm. And here what are we saying? Oh, there's no efficient algorithm, great, let's use that, right? So it's a way to make something very positive out of something that could, would otherwise have been only bad news. Okay, so this is the first idea that I wanted to show you. There are also sort of other cute, simple tricks that we can do. Like, for example, one simple thing that we do with this is, suppose I had three cards. Okay, let's say just Jack, King, and Queen. Okay, and two of us, let's say Ananya and I, we want to uh, come into agreement on some random string, which we then want to use as our key. Okay, so we want to agree upon this random string. So now let's say that, you shuffle these cards and you distribute. So Ananya and I, let us say, are the legitimate parties, and let's say that you're the attacker. So you want to figure out what our key is. So somebody has distributed these cards. Okay, now everybody has got either Jack, Queen, or King, the three of us. So it's this very simple, cute little trick that we could do. So how can we both agree on a key? Okay, here's an idea. I look at my card. Okay, let's say that my card is the King card. So I know that Ananya either has Jack or Queen, but I don't know which, right? So what can I do? I can just guess. I can guess that, let's say, I guess that she has the Jack, right? And I have the King. So what can I do? I will just shout and say, I don't have Queen. Just, okay? So I'll just say, I don't have Queen. And then she'll also look at her card. If she doesn't have, if she has Jack, she can also say, I don't have Queen. Now, we both know, right, that what is the other person's card. So let us say that my strategy for selecting a bit is that whichever is the, whichever, if I have the higher card, then the bit is 1. If you have the higher card, the bit is 0. Now, what did we do? We said that, I said I don't have queen. She said I don't have queen. What does that mean? It means that she has the queen. But she already knows that. She already knows that she has the queen. So she learned nothing. So we announced something in public, right? One moment. We announced something in public using which we both exchanged some important information, right? So now we figured she knows I have king, I know she has jack. That means that we have agreed on the bit 1, because we said that whoever, if I have the higher card, then the bit is 1. This was our strategy, right? And the third person did not learn anything. So this is a very simple trick, but a lot of ideas that we use in cryptography are like that, where we try to give out some information which is somehow useful only to the two parties that wish to cooperate. What was your question? We'll announce it. I'll announce it to everybody. Very good. So that means you have the queen, right? Oh, that doesn't work at all. No. You can guess, right, with probability half, right? But I'm going to do this 200 times, right? So the probability that you will guess correctly when I repeat this, if I repeat this 200 times, the probability that you will guess correctly is half to the 200, right? Very good. So in that case, we say we're just going to start again. We'll just discard this round. And in expectation to agree on k bits, how many times will I need to run this? What? So we'll shuffle and start again. We'll just throw that round away. See, it won't work. If I guessed wrong, then it won't work. It's got a half chance of working. Okay, and I'm going to repeat this k times for some k. Okay, so no, the way that we did it is, right, there is party 1, 2, and 3. So by the way, this is a totally toy example. I mean, of course, like in real key exchange protocols, we don't have these cards and so on. But the reason I find this example nice is that it illustrates the power of randomness, which plays a very crucial role in cryptography. You know, randomness is really our friend. So what are we doing in this is that, we are dealing out 3 cards to 3 people. Okay. And then if 1 and 2 are the people you and I want to exchange the bit, right? So what we'll do is I'll guess your card and I'll just shout, I don't have whatever I think this person's card should be. Okay. So I'll just shout, I don't have queen. If you also don't have queen, you'll say, I also don't have queen. What did this person learn? This person learns that neither of them have queen, but that it already knew because it has queen. So it's a very sort of simple but very cute idea. It shows, how randomness is so powerful. I'm able to make, again, you see, like there is no real asymmetry here. because it's a fair deck. I'm shuffling it, I'm distributing. But you see how by revealing a certain amount of carefully chosen information, I managed to do something which is very non-trivial, right? So once again, I managed to exchange a long sequence of bits by repeating this many, many times and throwing away the rounds that don't work, right? So by repeating this many, many times, I managed to exchange a long key, and now I can use this to mask my messages. You see? So yeah, again, I will say, like, the power of randomness is what I wanted to illustrate here. See, the power of randomness also plays a role in this more abstract setting which I showed you, right? Because it's really important that I choose my exponents at random. If this exponent is chosen from some, easy to guess set, then this problem is not going to be hard. The problem is only hard, if you choose it at random from a sufficiently large set. So I want like a large group order, and I will choose from that at random, right? Yes, this works. This is used in internet protocols, and sorry. So when I did g to the x, I'm operating in the group. So I have very deliberately not gotten into any particular group over here, right? There is a group, it has an operation, and the conjecture is that this problem is hard, for that group. Okay, so these are a couple of ideas. Both of them, I would say, are to me at least quite surprising, right? So notice that they are enabling now for you something that all of you said will not be possible, right? So we can suddenly start talking in secret, and everyone can hear everything, right? But only we both will communicate. Okay, so this was the first idea that I wanted to show you. The second idea that I wanted to show you is again something which appears very surprising at first. In fact, not only at first, even after 10 years of being a scientist in this same field, I still find it very surprising. Okay, so what is this idea? Now everybody knows the idea of a proof, right? What's a proof? There's a proof that there are infinitely many prime numbers. If I want to prove to you some statement, right, I will show you the proof, right? This was, I don't know, my inductive hypothesis. This was my base case. This was my induction step, whatever. I will show you the proof. Once I convince you of the proof, I have transferred knowledge of the proof to you. Now you can convince anybody else of this proof as well, right? But in real life, there are lots of situations where you want to convince somebody that a statement is true, but you don't want to tell them any of the information that made the statement true. So this is a bit paradoxical again. In fact, it's very paradoxical. But think about it. Okay, so in real life, let's say that I want to sort of do some financial transaction. Okay, and I want to convince you that you should talk to me because I have the money to do this transaction with you. But I don't want to tell you how much money I have. So I would like to convince you, right, that a certain statement is true. What is the statement? That there is more than so many rupees in my bank account, for example, right? I want to convince you that this statement is true, but I don't want to give you my bank account information for you to be able to check yourself. So is it possible? Now, let's again take a step back and look at it very abstractly. Is it possible for me to convince you of the truth of some statement without giving you, any knowledge about why the statement is true? Excellent point. So what he says is that, what if there's a neutral third party that everybody trusts? Actually, you know, in this kind of world, it's actually, this is called the ideal world in cryptography. This is the world that you always try to emulate. uh, so all of cryptography is going to basically assume that there is no such person, right? Because if there were such a person, right, then all these problems are simple. But we want to protect against any particular person. I mean, who would this person be? You know, like it will be the government, or it will be, you know, somebody in your company or your college or whatever. And you don't really want to trust any one person with all your secrets, right? So we would like to convince somebody of the truth of a statement, but without telling them anything about why the statement is true. So now, you know, since we're running out of time, let's again take a concrete, a very fun toy example here. Okay. So let's think of Sudoku puzzles. So now all of us know what's a Sudoku puzzle. So it's a 9 by 9 grid. It's broken into these, you know, 3 by 3 squares. And then, you know, in every row, every column and every subgrid, I should have the numbers 1 to 9, right? What? Is it 0 to, no, it's 1 to 9, right? Yeah. So, have you seen this example before? I think you don't. If you haven't seen it before, oh, okay, then yeah, sure. So, because it's a little hard to come up with if you haven't seen it before. So now we have the Sudoku puzzle. Okay, this puzzle is, again, it's, you know, it's out here on the board. Okay, so here we have a puzzle. Okay, this is my puzzle. Okay, I'm not going to draw all the, anyway, I don't have any numbers in my head for this. But the point is that, you know, this is some well-formed Sudoku puzzle. And now I claim that I know the solution to this puzzle. Now, what is a way for me to prove to you that I have solved this puzzle? I could show you the solution. Sorry? Knowledge is transferred in that, right? So that's what you were saying? Yeah. So I think, like, if you've never seen this idea of knowledge transfer before, it's quite surprising that there is even a demarcation between, you know, proof and knowledge transfer. Because like, think about it, right? The idea of a proof in the classical sense, in the standard sense, has the idea of knowledge transfer really built into it, right? That's how I prove things. How will I prove that I have the solution? It's by showing you the solution, and you can verify, right? You can verify that all the rules are satisfied, you know, and that means that I did not cheat. But now suppose I want to prove to you that I have the solution, but I don't want to tell you the solution. Is it possible? So, I mean, the answer is yes, because I'm here. But apart from that, you know, side information, that I wouldn't be bringing this up if I didn't have a way to do it. Should it be possible? So, who says it should be possible? And this is not based on prior knowledge. Yeah, so good. Actually, both of these are good points. So the one answer that was given is that I don't see any contradiction in this being possible. That's true. So, you know, it's not, you know, there's no immediate contradiction as such. But intuitively, as you said, intuitively, it seems that it shouldn't be possible, right? I mean, it's, again, it's something which you, if you just think about how would you do it, I mean, it's not clear what you might possibly do, right? Okay, but I'm running out of time, so maybe I'll lay it out a little bit more than in the previous case. Okay, good. So actually that's a good starting point. So the suggestion is that somehow maybe we can jumble up the boxes and sort of like maybe I'm somebody has the solution. So I let's say again we use cards, okay? So let's say that I have cards face up. So if there's a number 2 here, then I have a card face up with the number 2 on it, okay, and so on. And now his idea was that I want to jumble up the solution and give it to somebody to verify. So that intuitively it seems like something like that might help you, right? Because I just want to verify that the numbers 1 to 9 are there. So to implement your idea, let's say that the prover, that is me, I'm trying to prove to you that I have the solution. Maybe what I will do is I will take my solution. Again, I will use cards for it, right? So whatever are my numbers, I will take those cards and I'll place them face down. Okay, so I've placed my solution cards face down. And now, having done that, maybe I can also turn these cards down, and now I can jumble them up. So for a particular, let's say for a particular column, right, all the cards are placed face down. What could I do? Well, I can pick them up and shuffle them and then open them and show you that the numbers 1 to 9 are there, right? That was the suggestion which he made, and it's a very good one. Why is this intuitively useful? Exactly, because you, by virtue of shuffling, you jumbled up all the positions. Yeah, you only got to know that you have 9 cards, but you did not get to know where they were, right? But now exactly. Exactly. Good. So you people are solving this by yourself step by step, which is great. So he gave a great first idea, and now he at the back has a attack strategy using this, right? And this is exactly, even though these are toy problems, actually cryptography research is just like that. So you want to achieve something, and then you try something out, and then there's a problem, and then you try it out again, and then again there's a problem, and you keep going, and maybe at some point you succeed. So the problem that he pointed out is that well, I'm saying that I took these and I shuffled them, but I could be cheating while putting them back, right? So why is Sudoku hard? Sudoku is not hard because one column is hard, right? Sudoku is hard because I have to maintain consistency. For every row, column, and subgrid, I have to have consistency. So what should I do now? What? Of course, I mean, if you haven't seen it, of course you can say. Yeah? No. I mean, okay, so this is like a proof of smartness that, I will solve something else and show you, and then I will use that to argue that therefore I could have also solved this. But they could be of different levels of hardness. And anyway, like just because I solved that doesn't mean I can solve this. So good. This is the complexity theorist approach. Reduce it to a harder problem. Yes. Any other ideas? No, what you guys started with is actually the right way forward. I mean, yes, it's very natural to think that shuffling, especially because we used it so successfully in our key exchange, right? The power of randomness, right? So shuffling wipes out the information, but it gives me exactly the information I need, which is that, 1 to 9 is present. But like he said, the problem is that, what about consistency? I mean, okay, I did this for one row. So how about for each row, column and subgrid, I give you, a fresh card. Okay, so let's try to kind of build in more information into the system, because if I just say that I'm shuffling and putting it back, right? Then I could put it back in some cheating way. Like I'm putting it face down, right? So maybe I'm permuting it while putting it back so that it's not consistent with what other stuff I had before, right? So what I will do is I will say that, I will check simultaneously. But how will you show that they're equal? So, okay, so 1 second. So, first of all, 1 second. So, first of all, what we will do is simpler than what you're suggesting. Yeah. Then you're giving information. But you gave information. Yes. Give a zero knowledge proof that they are different. I'm trying to build a zero knowledge proof for a Sudoku puzzle. No? No. No, 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 no. This is total cheating. The one rule in this classroom is that everything is from first principles. We do not come in with, we don't even come in with hash functions. We definitely don't come in with zero knowledge proofs. No, so you know what like I was saying, I mean, what I'm showing you is a toy, illustration of how something like zero knowledge can work, right? If you've seen a zero knowledge proof, then you've seen something more formal than what I'm showing you. But I don't think you guys have seen a zero knowledge proof, right? But then if you ask me to solve this using a zero knowledge problem, like zero knowledge proof, then again, it's you're going in the opposite direction. So I'm trying to show you a simple illustration of how one might do it. I'm also running out of time. Okay. So let's do this. So we said that, since we want, yeah. Yeah, so something like that can be promising. Again, so using cards, what? So I didn't 100% understand what you said, but something where you take a random permutation, do some mapping, that sounds like it's going in the right direction. Exactly what you wanted to do with this card problem, I did not really follow. Yeah, that would work. Yeah, yeah, good. So, that's an idea that would work. Let's, let's see another simple way of making it work, just using cards, right? So, what I'll do is that for every row, column, and subgrid, I'll give you a new card. Okay. So, if I have two here face down, I'll put three cards, which are two, right? And I'll put them face down. And I'll do this for the whole grid. Now, what do I do? For every row, column, and subgrid, I make a packet. Okay. And I shuffle that packet. Okay. So, for every row, so let's say for this row, I take one card each from each cell. Okay. And I shuffle it, right? And I open it. Okay. And similarly, I can do it for every column, every subgrid, right? I could also just do it for a random number, a random set of them. But for simplicity, let's just say I'm doing it for all of them. Okay. In that case, I can check for each of these that, the permutation is very good. That's exactly right. Hang on, everybody. So I think, yeah. So the objection is valid. Okay, so the solution strategy that we were building is that since I don't want to just check a given row, a given column, or whatever, right? I will have enough cards to check each row, each column, and each subgrid. Okay. And now the strategy that I was proposing is that, for each row, column, subgrid, I pick up these cards, I make packets, right? I shuffle them and open them and show them to you, right? The problem that some of you were alluding to is that these could be inconsistent, because it could be that, like I said, even though I'm supposed to put the three copies of the same card in a given cell, I could be cheating, right? I could be putting them based on, like, so for the row, there's a different solution. For the column, there's a different solution, and so on. I could be doing something like that. So what can the verifier do in order to thwart this strategy? Maybe someone else? Any idea? Yeah. Okay. I mean, so that's a more complicated solution. So there, basically, you have to have some sort of secret mapping between every number and some symbol. So since we're out of time, I'll just give you like this final idea here. So we can just shuffle the cards in each cell, right? So if I have row, column, and subgrid, I just shuffle them. So if I had planned it so that, for the row, I take the top one, and for the column, I take the second, and for the subgrid, I take the third, then by shuffling them, when the cards are equal, I do not destroy correctness, right? But when they are unequal, then I introduce a probability that the cheating prover will get caught, right? So again, this is a toy example, right? But again, it illustrates the idea that randomness is very useful. Like if somebody is trying to prove something to you, right? Then randomness really helps the verifier in catching somebody who is trying to cheat by doing these kinds of tricks. So what I was saying was that for each row, column, and subgrid, in each cell, I have three cards, okay, placed face down, the same card. If I'm not cheating, it's the same card. I could be cheating by making them inconsistent. To thwart that, what you can do is for each cell, you can shuffle the cards, right? So I'll just shuffle. So if it's supposed to be 2, I'm supposed to put 3 copies of 2. Suppose I've cheated, I've put 2, 3 and 5. And I want you to take 2 for the row, 3 for the column and 5 for the subgrid, right? Then by shuffling them, I destroyed your solution strategy, right? And whatever shuffle I did, the new cards in the new position, right, will not give me a valid solution. Yeah. Yeah, sure. Yes. So what we're doing is already similar. I mean, basically, probability in this case helps you, right? So what we're hoping to do is kind of catch a cheating prover with some probability. Okay. And like you were saying, I mean, I don't obviously have to be working with cards over here. So, I could do something where maybe there's a random permutation that I choose, and every number I map it to this permutation, and I just give you the, so your solution idea was that I give you the permuted grid, right? What was your solution idea? But how will I prove that this is consistent? I mean, if I have to give you a full grid, right? Okay, sure. So, so the goal for us is to catch the cheating prover with some probability, right? Now, so in this idea, one needs to analyze, like, can the prover cheat, like with what probability can the cheating prover be caught and so on. But in general, something using random permutations, should work out. Yeah. I was thinking of the same thing, that basically then you're leaking information about your permutation, right? Because, yeah, you don't show. Yeah. No, no, no. But okay, so we can take this offline. But if I understood your idea correctly, what you were saying is that whichever number I take over here, I map it to some other random number, right? But then the worry that I have in what you're saying is that, let's say that in my permutation, 2 gets mapped to 5, right? Now the Sudoku puzzle is actually printed on the board for everyone to see. So you have to be careful. I mean, again, so it is not, if I reveal that, there is a 5 now in this position, right? Then that is leakage. Yeah, so maybe you have something else in mind. So that's what I'm saying, that you need to work out a proper algorithm, like what is it that you're going to do, right? And then you have to prove that there are these two properties we want to prove. One is correctness, which means that, as long as the prover is honest, the verifier believes the prover, right? And the second is what we call soundness, which is what we have been discussing all this time, which is that if the prover is cheating, then the prover should get caught with some good probability. Which money problem? Yeah, so that was just a motivation. So yeah, this card thing will not solve that problem. What? For what? Mm. Yeah, so good. So let's address this question. Okay. So the question is that, are you not going to be 100% sure, and isn't that a problem? Okay, so once again, in this toy example, there is this one Sudoku puzzle, right? And if I have some probability of cheating, then I have this probability of cheating for this. But in general, for in general, right, what is a natural way for me to bring down the probability of error? Just do it many times. Does that work also with this? Right? I can always repeat the thing many times, right? And if I manage to cheat every time, then only do I cheat overall. And then the probability that I cheat every single time is going to be small. Yeah. No, so this is really a toy example. So I mean, in real zero knowledge proofs, we could use computationally hard problems, but here we did not use any such thing. Yeah, sure. I mean, so in general, you can prove any statement. What's the question? So this does not solve that, right? But in general, there are ways of constructing zero knowledge proofs for general languages, which can be used to solve the particular question that you're asking. Whatever problem it is that you have, right? So for example, I could give you a zero knowledge proof for any statement of my choice. Okay, so we have to be careful here how we define the model and so on. Yeah, sure. Yeah, are there any other questions? Yeah. So good. So this is a good question. So in general, I want to say that the probability of error can be brought down to be so small that it is essentially zero. I mean, it is smaller than the probability that we'll get killed in the next moment by a random collision, or like it's a very small probability. Uh, I will get back to you on that. Okay, so yeah. So there are different parameters that we can have, right? Like there's a soundness probability, a correctness probability. So even so, generally you could construct schemes that have some probability even of not being correct, right? Some probability of allowing the prover to cheat, right? And usually we can manipulate these probabilities. Now, off the top of my head, I don't immediately remember, like, can this be one, this be one, and so on. I want to say yes, right? Because usually you can trade off these parameters. Um, but yeah, I cannot think of an example right now. Any other questions? All right. Thank you.